So I've done that. How much momentum is the dumbbell also?
Okay, you have done the dumbbell one?
Yes, ma'am. Yes, sir.
Okay. Okay, please do it, Harshita. After that, we'll start the second law of motion.
Okay, sir.
Okay. Did you revise, Harshita?
Yes, sir. I did revise.
Sure, that's good. Because the next topic that we will be doing is basically based on the momentum. That's why I was asking.
Okay, sir.
Okay, have you done the homework as well, Harshita? Actually, I was not able to check it, but right now after this class,
I
I'll be
did.
having. Okay, check it. That's good. So I'll be checking the homeworks, all the pending homeworks. I'll check it by tonight, and will update you. Like you will get the notification on the portal itself. Okay,
Okay, sir.
check it. Good. Just a second. Sure. Give me a second. I'm turning on the video. Just allow. Then Harshita, answer.
Sir, I did the first time doing the C part.
Acha, chicken, do it.
Yes, sir.
Yes, Harshita, tell me the answer.
A is 50 kg meter per second.
Correct. Second,
Second is 0.2 kg meter per second.
0.2. Point
Is
two. Huh, chicken. No, I don't think so. Point two. It would be 100 na, so it would be point two into 10. It should be 2. Point
mm,
two into 10. Isn't it should be 2 na?
no, sir. It will be 0.2.
Why? 20 divided by 100. So point 0.2 meter per second is the speed. Now you have to multiply it with 10. So point 0.2 into 10 would be
Okay.
2 kg na? 2 kg meter per second. Got it?
Yes, sir. I got it.
Yeah, next one.
The next one is 100 kg meter per second.
100.
Yes, sir.
So it would be 5 by 18 to 10, 100. Yes, that's right. Very good, Harshita. Very good. Okay, now let's start. Okay, just let me check one thing that if more questions are there based on that, we'll do it first. And so what about the worksheet? Did you practice it again or not? You can practice it 2 to 3 times at least. Okay, so that you can get the idea. Okay, na?
Okay, sir.
Yeah. So please
Sure, sir.
practice this twice or thrice.
Okay, sir.
Just a second, sir. Let me just check. Okay, Arshit, I don't think there are like more questions based on that because ultimately this type of question can be done. Okay. Now let's talk about the second law of motion. Okay. So second law of motion is a very important, you can say that the topic that we are going to discuss in this class, Harshita, because this topic is very popular and famous, and most of the question from the force and law of motion comes from this topic. F equals to ma. You might have heard about this equation. F equals to ma. Force is equal to the product of mass and acceleration. How do we get it? Let's take an example, Harshita. I will not basically tell you about what it is written. No, I'll explain you the example first. Then we will go through the you can say bookish language, or you can say the context, basically context. First of all, let's take an example, Harshita. Suppose there is a body of mass m. It was already moving with the initial velocity u, right? So what will be the initial momentum?
Init-
Mass is m, initial velocity is u.
So it will be mu.
Mu. Simple. Okay,
Yes.
so after that, suppose let's take an example. Instead of a body, let's take a car. Okay, car was moving with a velocity u, initial velocity, and of mass m. Right. After that, after some time, what have you done? Basically, you have pushed that car with the hands, right, for a time t. Obviously, when you are applying force, it is basically you are applying for a minimum, basically specific time, isn't it?
Yes, sir.
Right. So that's why. So Harshita, when you will apply the force, will the velocity of the car will change or not?
Yes, sir. It would
It
change.
will change because an inertia, in law of inertia says that if the external force is applied, then the state of the body would change, right? It will come
Yes.
to accelerated when you will apply the force, obviously, right? So basically, Harshita, when you are applying the force, the velocity is changed to v. Instead of u, it's coming to v. Obviously, mass would remain same, m. No need to write it, Harshita. I'll explain it. No need to write it. Just taking an example, just understand. Okay, so
Yes.
what will be the final momentum then, Harshita?
If it will be mv.
Mv, simple. So now,
Yes.
Harshita, if you see this thing, if there is a change of momentum, because there is a change of momentum means if you basically subtract the final minus initial, you will get a value because velocity is increased. So obviously momentum will increase, isn't it?
Yes, sir.
Great. So Harshita, the second law of motion says that if the change of momentum is very fast with a very small time, I mean saying in the general language, definition is something else, but the summary is the, you can say the extraction, the ultimate understanding of this statement is if the change of momentum is very small, sorry, basically the change of momentum is there and it has done in very small amount of time, then the force would be very large. Suppose that, let's take an example, Harshita, again. Suppose a person is traveling in a car. Two scenarios are there. First one is seat belt is there. Second one is seat belt is not there. Let's take an example that seat belt is not there. So suddenly you are basically the person is going in a car and suddenly the brake has applied by the driver, right?
Yes, sir.
So what would happen, Harshita, after the applied the implement of the brake?
You would go forward.
We would go forward. And Harshita, you might see this say the thing, if the brakes are applied very fast and obviously the change in momentum is in a fraction of second, like 0.1 second or 1 second maybe. So your body will go very fast and the person might get severe injuries and maybe death. That happens in a road accidents, right?
Yes, sir.
Second thing, if there is a seat belt, Harshita, so
Yes, sir.
what would happen if the change of momentum is basically change of momentum is there, but seat belt is there. So when you will go there, the seat belt will stretch it and will in decrease your forward movement. It will slows
Yes.
down. That means the
Yes.
change of momentum is there, but the time taken is more. And in the first case, time taken was less. Clear?
Yes, sir.
Just give me a second. Actually, someone is the door. Just give me.
Okay, sir.
Okay, sorry for the interruption, Harshita. Yeah. So what I was saying,
Yes.
so we have two cases when there is a seat belt, when there is not a seat belt. So in which case the injuries would be large? First one or second one? Seat belt is
The
there.
first.
seat belt is there, that's the second one. Seat belt is not there, that's the first one. So in the first case, obviously, and it will be basically happening in a very fraction of seconds, right? Because there is no
Yes,
support, that will basically increase the time of change, right? So I hope that's clear.
yes, sir. It is clear.
So that's what second law of motion says. देखो, if I tell you that this is the definition, this and all that, you will understand it, but the major implementation will not be understood,
Okay, sir.
right?
Yes,
That's why I've taken an example. I hope that's clear to you.
yes, sir. It is clear.
Or now let's take an example, Harshita. You must have like, have you ever watched a like, ever seen basically you can say match of cricket match, something like that,
Yes, sir. I have.
right? So when you see this thing, there's a basically keeper who is basically standing behind the batsman to catch the ball, right?
Yes,
Ball is coming very, very fast. So every see this thing, Harshita. Let me just show it to you with my hand. So when the keeper catches the ball, it takes the hand in the backward. He takes the basically hands in the backward direction. Why? Let me tell you. If the keeper does not takes the hand in the backward direction and just catch the ball, what would happen, Harshita? The change in momentum is there, but the ball in the last second, the ball was having velocity. In the next second, ball velocity is zero. So time is 1 second, right? That
yes,
means, according to this definition, according to this statement, if the denominator is a small, the force would be impacted large. That means force would be large,
yes, sir.
right? But if the keeper takes the hang in the backward direction, instead of changing the momentum in 1 second, it is taking 3 seconds. Obviously, it would decrease by 3 times. See this thing, how much it will affect. That's why whenever we are catching whenever we are basically catching, whenever we are stopping a high speed thing, high speed moving body, we take the hands in the backward direction.
Okay, sir.
I hope that's clear to you, Harshita, why I'm saying that.
Yes.
Any doubt so far to you, Harshita?
No, sir.
Sure.
I'm sure, sir.
ठीक है. So it says that rate of change. Rate means, Harshita, whenever the word rate would come, it means that that quantity is divided by time. I've said to you in the motion chapter as well, rate of change of velocity, rate of change of distance, speed, rate of change of
Yes,
velocity
sir.
is acceleration. So rate word is always there, right?
Yes, sir.
I hope it's clear.
Yes, sir. It is clear.
Okay, so that's what it is. Please do let me know if it's clear to you.
Yes, sir. It is clear.
So it says that rate of change of momentum of a body is directly proportional, means if the change in momentum is large, that means force would be large as well. That's what it's saying. Okay,
Okay, sir.
obviously, okay.
Yes, sir.
And it takes place basically wherever you basically apply the force. The change in momentum will take, obviously, when you are pushing a car, Harshada, it's already moving forward. So when you're pushing, the car will also move forward now in the same
Yes,
direction. And it is the direction of force as well, isn't it?
yes, sir.
Force, displacement. Yes or no, Harshita?
Yes, sir.
It's That's what the second equation is or statement is. It says that the rate of change of momentum is directly proportional to the force applied or applied force, and it takes place in the direction of motion, or you can say car or body,
Okay, sir.
in the direction of displacement motion in which the force acts. Clear, Harshita? Please note
Yes,
down
sir.
this one. After that, we'll do a derivation, small derivation, three line eq derivation, and this is a very important. Now the question will how like let me tell you how the question will come. State the second law of motion. Show that the force is the product of mass into acceleration, or it could be rephrased as, show that the force is directly proportional to the rate of change of momentum. That's how
Okay,
the
sir.
question would come. Okay, so you have to
Yes.
write down this statement. After that, we'll discuss that derivation. It's a small derivation. It's a very important topic, Harshita. Please and please revise it at least 2 to 3 times.
Yes, sir.
Have you done this one? Just write down the first part, this, till this.
Yes, sure. I wrote it.
Okay, that's great. Now let's understand. Okay. Now suppose that a car is moving with a velocity u and the mass is m. Okay. So initial momentum would be mu, isn't it, Harshita?
Yes, sir.
And the force, and obviously, if I'm saying that I wanted to change a velocity, so I need to apply a force. So a force is acting on a body for a time t, so that the final velocity is changed to v. That's the thing that we have just discussed orally. So this is in the written form. So the final momentum would be mv, isn't it, Harshita?
Yes, sir.
Okay. So now, Harshita, if you would take out the change in momentum, what do you mean by change in momentum? Final minus initial. So how would you write it? mv minus mu. Yes or no?
Yes, sir.
Now just substitute it over the values. Force is directly proportional to the change in momentum, that is mv minus mu upon t, the rate of change of momentum. Got it?
Yes, sir.
Yes or no? Got it?
Yes, sir. I got it.
Next is, Harshit, the next step would be, if you take m common, v minus u upon t, which quantity is represented by v minus u upon t?
The acceleration.
Acceleration. That means, Harshita, now force equals to v minus u can be substituted by acceleration, and hence it would be written as F is directly proportional to ma. Now, so you would say, sir, how would you like we usually use F equals to ma? There is no equality sign. So what would you do, Harshita? Whenever we basically remove the proportionality sign, a constant would appear. Okay. And according to scientists, the value of this constant is 1. So that's why 1 into ma would be m into a. That's what the equation is. Please do let me know, Harshita, if it's clear to you or not.
Yes, sir. It is clear.
Okay? Sure, that's
So,
great.
so the
Ah,
constant value will be represented as k.
yeah, basically, in like it's for every equation, the constant is different, Harshita. For this equation, the constant is k, and it is the value of this constant is 1.
Okay, sir.
Yeah. Okay? Please note it,
Yes, sir.
Harshita.
Yes, I finished it.
Okay, Harshita, that's great. Okay. Now let's understand it. Okay, Harshita. So what basically Newton's second law of motion gives us the relationship between the force and acceleration, because mass is constant, Harshita. Mass does not change very like of a same body. It's only thing would
Yes,
change force and the acceleration. If you increase the acceleration, force would change. If you decrease the acceleration, force would change. So both thing happens with the force and acceleration only. Next thing is,
yes,
Harshita, suppose that if I write down, can I write down this thing equation as F A is equals to F by M? I've just
yes,
divided the force by mass. I will get acceleration. So Harshita, from this thing, you can see that force is acceleration is directly proportional to the force. That means, Harshita, if you increase the force, acceleration would increase. Yes or no?
yes, sir.
But here, if you decrease the mass, the lower will be the denominator. In that case, the overall acceleration would increase or not.
Yes, sir.
If right, but if the force remain constant, but we increase the mass, what would happen, Harshita? Could you please tell me?
The force would be lower.
Accelerate. No, no, we are not talking about force. We are just talking about acceleration, because force is constant. Because Harshita, whenever the two quantities are on the same side, they are not dependent on each other. The quantities on
Okay,
the one hand, on the other hand, depends on each other. Right now, acceleration and mass is there. Force is constant. We are saying there is no change in force. We are just increasing the mass. What would happen to the acceleration?
the acceleration would increase.
Decrease, Harshita, because the denominator is there. Now, if you increase the denominator, what would happen? The fraction would decrease or increase. See this thing. If I'm writing 1 by 10, again I'm writing 1 by 100. Which one is bigger?
1 by 100.
1 by 10.
1 by 10.
Point 1, point 0.01. Obviously, this one is bigger, Harshita. So the
Yes,
more the denominator would be, the less will be the fraction. And less the denominator would be, more will be the fraction. Got it?
yes, sir.
So that means, Harshita, if we take the case, if same body is there, the mass would be unchanged. Only thing could be changed is force. So acceleration will directly depend on the force. That means force increase, mass acceleration would increase. But
Okay, sir.
if we change the scenario, now the force is constant, mass is variable. That means we are taking two bodies. So mass increase the mass, less will be the acceleration. Decrease the
Okay,
mass, more will be the
more
acceleration.
will be
That means,
there.
Harshita, lighter mass will have more acceleration as compared to heavier mass. So you must have known that. See, you must have seen this thing. A bus will take more time to accelerate as compared to car or a bike. Yes or no? It
Yes, sir.
take like it look like the bus is very slow, but it takes time because mass is heavier of the bus. Got it?
Yes, sir.
That's what it is. Okay. So force is a
Okay,
vector quantity and the unit of the force is Newton. And if we basically, if the question says that define 1 Newton of force, what it would be? It says that 1 Newton of force when it is acting on the mass of 1 kg and producing an acceleration of 1 meter per second square. Is that clear, Harshita?
yes, sir. It is
Okay.
clear.
I hope any no doubt is there to you.
No, sir.
Sure.
Yes, sir, I'm sure.
Okay, please note it down. After that, we'll discuss the applications, and after that, we'll do the numericals based on that. Numericals are important, Harshita, because numerical would test the equations of motion and the force topic as well.
Okay, sir. Yes, sir. I completed it.
Okay, Harshita. Noted down this one, the last point as well.
Yes, sir.
Check it. Just give me a second. Okay, Harshita. Now let's talk about the applications of the second law of motion. First of all, as I've said, the catching of a cricket ball. Whenever a person is catching, it takes the hand in the backward direction, right? To avoid the injuries to the hand. Okay, why? A fast moving ball has a large momentum, and stopping this ball, the momentum is reduced to zero. So when a cricket player moves the backs his hand, okay, on catching a ball, the time taken would increase. So time taken increase, so force would decrease. Got it?
Yes, sir.
Okay, and hence that's why the less amount of force is acted. That's why we do not get hurt while catching the ball. Okay, please note it down, Harshita. This is the first. I know these are some. This is a 3 marker question, Harshita. In the exam, the question will be coming directly. Why the keeper or basically a cricket player takes the hand in the backward direction while catching a ball, or explain it with the help of second law of motion like this. Conceptual
Okay, sir.
questions carries very high weightage. Okay, I hope that's clear to you.
Yes, sir. Yes, sir, I finished it.
Okay, just wait for 2 minutes. Actually, it's Azan right now. Just wait for 2 minutes. Once it complete, we'll start. Just 2 minutes. Okay.
Okay, sir. Sir, can we start?
Yes, Harsh. Now it's over. Yeah. Okay. So second is use of seat belts. So in the last, as the example, Harshita, I've given you the idea that why do we use seat belt? We use seat belt to basically increase the time of forward movement. Because if the person basically, you can say suddenly crashes with the dashboard or anything that is maybe windshield as well, like that. So there might be basically severe injuries to that person. But if there is a seat belt, it will reduce the amount, right? Because it will basically increase the time, and hence we will basically slowly round to that, and it will leads to very minor injuries of to that person if the accident is happened, right?
Yes, sir.
That's why the seat belts are introduced, and that's why you must have seen that if you do not wear the seat belts, there would be a fine for like the for the driver, for like for everyone in the car, because seat belts are made for the safety. That's why it's very very important to wear the seat belt whenever you are also in the car or a bus. Always wear the seat belt. Okay, Arshita, please note it
Okay.
down. Thank you.
Yes, sir.
Okay, Harshita, that's great. Okay, Harshita, would you like to try this question that forces needs to be calculated and acceleration is 4 meter per second square and the mass is 6 kg? Basic
Yes.
calculation, F equals to ma, just let me know.
Okay, sir. The force will be 24 Newton.
Yes, Harshita?
24 Newton.
That's right. That's right. 24 Newton. This was a basic question. Try this one and let me know the acceleration. Mass is given, force is given. Acceleration would be